Hey, Physics 30, so we're going to go over assignment number 1 here. Seems like a pretty straightforward assignment. Here they just want to calculate the visible range, or the energy range of visible light, which has a wavelength of 400 nanometers to 700 nanometers. So pretty much accepted values. Sometimes you could say 750-ish for the top range, and maybe 350 or 380 for the bottom range. But these are pretty good numbers. So we are going to calculate the two energies, and we can either calculate them in electron volts or joules. Joules is more useful for calculations, doing additional math, and electron volts is more useful for just simple communication. So I'm going to use electron volts here to calculate the energies. So to calculate energy of a photon, I'm going to use E is equal to H times F or HC over lambda, depending on what we have in the situation. This one we have wavelength, so I'm going to use the HC over lambda. I'm going to be using the H value, the 4.14 version, because I want this to be in electron volts. To the negative 15, I believe. Okay, maybe I'll make that a little bit nicer, a little bit bigger. Right up here. So 4.14 times 10 to the negative 15. I'm going to use the speed of light, obviously. It's 3 times 10 to the 8. And I'm going to divide by my nanometers. So this is the red one we're doing first, so 700 nanometers. So I'm going to change that into meters. And I'm just going to punch this in my calculator and see what we've got. 1.77 electron volts. Okay. For the other side here, we are going to do for the violet light. So the wavelength on this side is the 400 nanometers. So I'm going to go HC divided by 400 nanometers. So I'm not going to bother writing in the HC again. But I can just go to my calculator and just change one number here to 400, and I get 3.11 or 105 electron volts. Okay, which makes sense because the violet light is more energetic because it has a shorter wavelength. And the range that I have here, I'm just going to take one number minus the next number, just to find the difference between the two numbers here. So I get 1.33 electron volts is my range. I'm good. Okay, what's the wavelength and energy of a 92.1 megahertz photon? Okay, so that's probably not visible light, but that's fine. So the first thing we're going to do, maybe I can determine what the wavelength is. So remember, I can find the wavelength of a photon. If I know its frequency, I could just use the universal wavelength formula. So we're going to go C divided by frequency, which is going to be 3 times 10 to the 8 meters per second, divided by the frequency of 92.1 times 10 to the 6 hertz. So that's what a mega is. All right, so type that in my calculator. Yeah, awesome. So we get a wavelength of 3. It's a nice number. 3.26 meters. So it's a rather large wavelength, but you have to imagine that even though the wavelength is 3 meters long, the photon itself is infinitesimally small. So it's behaving as if it has a large wavelength, even though it's technically not the size or bigger than me. Okay, so it's definitely not 3 meters long. Here we're going to do our energy. Again, I can just use the communication purposes. I'll just use electron volts for this one, unless it specifies otherwise. So I'm going to be using the 4.14 number again, because it says electron volts per seconds there. And I'm going to be using the frequency here of 92.1 times 10 to the 6 hertz again. Okay, so these are not going to be very energetic. It's a very large wavelength. So it's not going to be a very large number. That's fine. Let's have to live with that. It's actually 3.81 times 10 to the negative 7 electron volts. Very small number for this one. You can change that into nano electron volts. You can do a bunch of things. I'm just going to leave it in that form. If you want to, we can also change this into joules. I might as well just do that. So I'm going to times it by the conversion of 1.6 times 10 to the negative 19. And I'm going to get 6.10 times 10 to the negative 26 joules. So here I just times by 1.6 times 10 to the negative 19. I like that. That looks like a happy face there. That's how many joules for every electron volt. There you go. What's the threshold frequency of a metal? It was a work function of 2 electron volts. So remember, that's the amount of energy required to emit an electron. That's the amount of energy a photon required to emit an electron. So we can use the formula. W is equal to HF. It's the same formula as E is equal to HF. But instead of E, we just use the W because this is the work function. It's the same formula. And I can just rearrange this, W divided by H. And because it's electron volts, I'm going to be using the 4.1 number again. Electron volts per second. You can look at the units there. The electron volts are going to reduce out. I'm going to be per second, which is a frequency. So 2 divided by this 4.14 e to the negative 15 will get me 4.83 times 10 to the 14. Oh, I was saying right, hertz. What is it? Hertz. There you go. The work function of a particular metal is 3 electron volts. Will visible light that has a frequency of 8 times 10 to the 14 cause photoemission? So there's 2 ways to do this. You can either determine what the threshold frequency is and see if that's enough frequency, or determine how much energy that photon is and see, is that enough energy? So what I'm going to do is I'm going to change this into energy. So I'm going to be using H times F here. I'm going to be doing the 4.14 number again because I want to compare the 2 numbers. And this one's in electron volts already. And then I'm going to multiply by 8 times 10 to the 14. Hertz and the per seconds will cancel out there. Negative 15, I should probably put in my calculator. And times by that. So what we get here for the energy of this photon, we get 3.312 electron volts. So this photon, the photon energy, exceeds the work function. So yes, photo emission will occur. Cool. Calculate the maximum speed of a photoelectron emitted from a metal whose work function is 2 electron volts when illuminated by light of frequency. Okay, so to find out the speed of this, I need to find out the kinetic energy, my EK. That's a really big K there. Okay, because I'm going to be using to find that, or after I use that, I can use this 1/2 mv squared formula to find the speed. But to do that, I'm going to have to determine the kinetic energy. So I'm going to have to use this formula that says that the energy of the photon is equal to how much energy goes into getting the photon or the electron out, plus how much energy the electron has afterwards, the kinetic energy. So the energy in has to be equal to the energy out. So a photon comes in, and then when it gets absorbed by the electron, a little bit of it is used to dig the electron out, and then what's left over is used as kinetic energy. So before and after have to be the same. So I am going to determine, the EK. I'm going to determine the EK in electron volts here. So I'm going to go the photon minus my work energy. I have to determine the photon's energy, so I'm going to go H times F minus this 2 electron volts that I have here. So the H times F, I'm going to have to use the electron volt version because I want to compare these two numbers, is 10, is a high frequency, okay, that's the reason. So it's 10.35, and I want to minus the 2 electron volts. So the electron uses 2 to get out of the metal, and then I subtract 2, and it has 8.35 electron volts of energy as kinetic energy, because that's what's left over. So this energy is going to be converted. I'm going to convert this into joules because that's the only way I can use it for the math here. So it is 1.336 times 10 to the negative 18 joules. And then I'm going to use that in the rearranged formula here to determine the speed. Okay, so 2 times this 1.336 number. Oh, my head's getting in the way here. Yeah, my head is getting in the way. Divided by the mass, 9.11 times 10 to the negative 31 kilograms. Take the square root. Okay, so times it by 2. Got the number in my calculator, so that's what I did. Divide by 9.11, e to the negative 31. Take the square root. It is going at a speed of 1.71 times 10 to the 6 meters per second. Ooh, that's quite fast. It's really, really high frequency on that. Photoelectric experiment is observed that no current flows and that the wavelength is 570 nanometers. What is the work function? So that, remember, the wavelength can be converted to frequency pretty easily by using f lambda. I can say f is equal to c divided by lambda. So I'm going to go 3 to the power of 8 divided by, I'm actually going to write that in there, divided by my wavelength. I'm going to change that into regular meters. So I get a typical wavelength of 5.26 times 10 to the 14 hertz. Okay? So that is the frequency. This is the threshold frequency. Didn't quite ask for that number, but I'm going to put that there. That's the frequency of the photon required to get this to work. And then I can use that in this formula. I could have just used the wavelength as well, but I'm going to use the I'm going to use the frequency to do this one. I'm going to use the H for the EV because that's the better way to communicate these kind of numbers. And I have this number here. I got the number in my calculator, so there's more decimals to this than what you see, what I wrote down. And times them together. And I get a work function of 2.18 electron volts. There you go. Hopefully you did well, and I'll see you in the next video. Bye.